everybody, this is Mrs. Ewald signing in, and today we're going to talk about energy diagrams. You might remember we talked about energy diagrams a long time ago when we talked about thermal chemistry, specific heat capacity a little bit, and we also just previously talked about rates of reaction, what can increase the rate of a reaction, and we mentioned activation energy. You might remember that from biology as well. You learned about activation energy and the amount of energy required for a reaction to go. So what I want to do is go through an exothermic and an endothermic energy diagram. You need to make sure that you draw these out, that you label them, you know all of the parts, and you're able to answer questions that correlate with them. So take your time, pause, stop, do whatever you need to do to make sure you have a full diagram of both the exothermic and endothermic reaction. So to start off, let's look at the exothermic. In an exothermic reaction, we know that energy is going to be produced, so you have a net gain of energy at the end of the reaction. So let's just go through the anatomy, we could say, of an energy diagram for an exothermic reaction. So looking at here, notice you have on the x-axis the reaction coordinate, and so this is going to be the amount of time that's occurring. So when you read it from left to right, so we are assuming then it's going from reactants to products. So I'm shortening this R meaning reactant, P meaning product. So starting off, you have the potential energy, and here the unit is in kilojoule per mole, so how much energy per mole. And on top here, this first line is showing you the amount of energy to start with. So this is the amount of energy in the forward reaction of your reactants. And then as time goes by, you're also able to see a few things. So you're able to see the activated complex. And so right around here, we refer to this as the activated complex. And so that is the peak. Okay? And then it's going to slow down, or as the reaction keeps, you have a lot of stuff going on here, it's going to move down and then end into your products. So this here is the energy then that your products have. And so if you were to subtract that, you end up then with a negative delta H, because it's a negative, meaning that you have energy that is being released. Okay, so let's go through all of the parts here. So let's just start. First off, the way that this is drawn here is showing you without a catalyst being added. And so you may often see a dashed line as well. And that dashed line would show you then with a catalyst how it would lower the activation energy. So you remember catalysts, oops, get rid of that. Exit. So a catalyst is going to lower the activation energy. You could also show that as E subscript A. And so it's going to lower that, which is what you are able to see with the dashed line here. All right, so A. A is pointing to the activation energy. And so from here to here, oh boy, having no luck today. So from here, from the peak activation complex down to the energy of your reactant, all of this would be the activation energy for an uncatalyzed reaction. If you had a dashed line here, then from here to that peak, that would be the activation energy for the catalyzed reaction. So you could have activation energy for both catalyzed and uncatalyzed. So you would look to see for the solid line, and also if it's provided for the dashed line. B. B is showing you the potential energy of the reactants. So that is from 0 up to the amount of energy that you have to start with. And so potential energy is always starting from 0 up, and you just read it from your graph. C is showing you your delta H, so your enthalpy. so the amount of energy that's either being absorbed or released. And so the delta H for this one would be negative delta H because it's exothermic. And then the letter D is showing you your activated complex, so from 0 all the way up to your peak. So that's your activated complex, the potential energy that's required for the reaction to go. E, so from your products up to your activated complex. E is the activation energy then of the reverse reaction. So you could look at this in two directions. You could look at it forward, or you could also look at it as a reverse reaction. And so what that means then is that these would be the reactants and that would be the product. And so in a reverse reaction, you could also determine the activation energy and so forth. And so if this now is your reactant, from this line up to your activated complex of your uncatalyzed here, that would be your activation energy, which is E. And then F is the potential energy of the products in the forward reaction. So in order to answer these, for example, on a worksheet like maybe tomorrow, you will always kind of be shown, if it's not mentioned, you could assume it's a forward reaction, but it may also tell you that it's a reverse reaction. So you have to be careful of that in order to know if it's talking about the activation energy of the reverse or the forward, because that will be different. Because obviously this is a whole lot different than this, what we saw earlier. Because in the reverse reaction, it ends up to be an endothermic reaction. And so let's talk about endothermic. So the next part shows you an endothermic reaction. So this is when energy is used. And so this again would be our forward reaction. This is the energy to start with, so these are our reactants and the energy that we end with in our product. So make sure you can identify, again, just as we did in the first, the activation energy. So the activation energy is from the energy starting with our reactant, so here, up to the activated complex. Now here again, we're only showing you an uncatalyzed reaction, but I could also change that and show you too a dashed line signifying a catalyzed reaction. Okay, so you always have to be careful of that. So from here to here, which is what we see in A, that is showing us the activation energy. Again, that is for the uncatalyzed. But if a catalyst is used, then you would lower that activation energy and it would only go to that dashed line. The potential energy of the reactants is B, so from 0 up to the amount of energy that your reactants have to start. C is your delta H. Again, it's your products and then minus the reactant, and so you end up with a positive delta H because it's endothermic. Your activated complex is from 0 up to your peak, and so that would be D. And your activation energy of the reverse reaction, to go in the reverse, this now would act as our reactant, and this would be our product. So in the reverse reaction, our activation energy would be from the reactant here up to the activated complex. And so this here would signify, your E, would signify the activation energy of your reverse reaction. And then lastly, the potential energy of your products would be F, so of your forward, so from 0 up to the energy of your products. So overall, you need to be able to draw you need to be able to draw energy diagrams of both exothermic and endothermic. Make sure you can label your axes and know what your units are. Be able to identify the different parts. So you should know activation energy, potential energy, activated complex, be aware of reverse reactions, as well as figuring out your enthalpy. So I think I have covered everything. Beware then for your energy diagram worksheet to kind of go through, and you're going to want to have these to look off of. So make sure you have really, really nice labeled energy diagrams. This is Mrs. Ewald signing out, saying happy energy diagramming. Bye-bye.